Okay, for this lesson we're going to be doing something a little bit different. Here I'm working from the PDF file, which is the handout for the lesson. This is a self-directed lesson, but I also thought it would be useful for me to provide a walkthrough of what you should be looking for and the things that you should be making note of as you go through here. So let's start with the basics. We're looking at exponential functions, and in particular we're going to start off looking at the exponential function y equals 2 to the x. So I'm going to graph this on the grid to the right. Fairly standard set of values I'm going to use here. For my x coordinates, I'm just going to start at -3 and go to +3. For my y values, let's start with the easy ones. So we start here with 2 to the 0, which is equal to 1, 2 to the 1, which is equal to 2, 2 to the 2 is equal to 4, 2 to the 3 is equal to 8. For these negative values, I might remind you that, for example, 2 to the -1 has the property that we take the inverse, or not the inverse, the reciprocal of that. So 2 to the -1 is the same as 1/2 to the +1, which of course is just equal to 1/2. 2 to the -2 is 1/2 all squared. There's another way we could write that. We could write that as 1 over 2 to the 2, and that gives us 1 over 4. So here we end up with 1/2, 1/4, and 1/8. Now trying to graph these, this is one of the things you'll notice when you're graphing exponential functions, that as you get to more and more negative values of x, so as you go this way, or as you get into greater values of x, the scale starts to become a real problem. On the lower end, you start to get these increasingly small fractions. And so I can graph this. I can graph when x equals 0, I have a value of 1. When x equals 1, I have a value of 2. At 2, I have a value of 4. At 3, I have a value of 8. 1, 2, 3, 4. Just put a little bit of a scale on there. There's 5, 6, 7, 8, 9, 10. Okay. So now that I've put a scale on there, what about going to -1? That's a half. Well, I can do that. -2, well, halfway in between, that's a quarter. -3 is an eighth. We start to get to the point where it becomes very difficult to do any real justice to what we're trying to draw here. And now we try to draw a smooth line to connect our points. An arrow there, an arrow here. We don't cross the x-axis. What we have instead is a horizontal asymptote and at y equals 0. So we have a horizontal asymptote here, which has the equation y equals 0. Now, what are the key properties of this graph? I guess we need to keep it in sight for now. The domain of this graph is going to be x member of the real numbers, and that's it. We can put any value in here for x that we want to. So the domain extends in both directions. What about the range? Well, in this case, we have a pretty clear indicator for the range. It's made up of real numbers, such that, but in this case, all of my y values are always going to be greater than 0. The x-intercept would be where it crosses the x-axis, but in this case it does not cross the x-axis, so I'm going to say none. It has no x-intercept. The y-intercept is where it crosses the y-axis, which is at the point 0, 1. Vertical asymptote, well, there is no vertical asymptote. There's no value of x where I'm not allowed to go. I can keep putting in bigger values, 3, 4, 5, 6, 7, 8, keep going up there. So just as was the case with the x-intercept, it turns out there's no vertical asymptote. The horizontal asymptote, we already said, was the equation of the line y equals 0. And the behavior, increasing or decreasing. Now, when we talk about increasing or decreasing behavior, what you want to do is you always want to be looking. So when we're looking at behavior, we always want to be looking from left to right. And so in this case, as we go from left to right, it's easier if I start, let's say, around here. As we go from left to right, I go to the right and it goes up. I go to the right and it goes up. And I go to the right and it goes up. Every time I take a step to the right, it goes up. That is an example of a function which is always increasing. Now, if we had something that was sometimes increasing or sometimes decreasing, we would specify when it was increasing and when it was decreasing. But in this case, it's always increasing. Okay, now we're going to get into the real gist of this lesson, which is transformations. Now, transformations is something that we covered in my course in a previous unit, so hopefully if you're taking a look at this, you have some familiarity with transformations. So take a look at what I've got written here, and hopefully that seems somewhat familiar to you. Y equals 2 to the x plus 1. So if we keep in mind that 2 to the x is the parent function in this case, then what we're really saying is we've got the parent function plus 1. That's what we're doing here. We're transforming the parent function. Well, what is that transformation? That is a vertical shift up by 1. So what is the graph of that going to look like? Let's go back to our parent function and imagine we took this entire graph and just shifted it up by 1 unit. What effect would that have? And so hopefully you can visualize the result that that's going to have overall. So let's see, I'm not so as familiar with this software. I'm not seeing anything so nice as that ruler is for measurement. I was hoping to be able to draw a straight line here, but I'm not seeing anything obvious to help me do that. So I'll do this by hand. So the first thing is the horizontal asymptote, which used to be along the x-axis, has now moved up by 1. So I'm just going to freehand this in, if you'll forgive me. So there, we have shifted the horizontal asymptote up by 1. So now we have this horizontal asymptote at y equals 1. And then all of those other points we had also get shifted up by 1. Now we could go back to the table of values, or we could regenerate a table of values, but the idea is that the overall graph is going to move up by 1. Now, one of the key points on the exponential graph is this one, which is the Y-intercept, and that occurs at the point 0, 1. So that's started at 0, 1. If we move that up by 1, instead of at 0, 1, it's moved up, it's now at 0, 2. Similarly, we used to have a point at 1, 2, but that's moved up by 1. Now it's at 1, 3. We used to have a point at 2, 4, but that's moved up by 1, so that's now at 2, 5. We used to have a point here at negative 1, a half, but instead now that's at negative 1, 1 and a half. And you can see that's a half a unit above the new asymptote. And then we will have one that's a quarter unit above the new asymptote and an eighth of a unit above the new asymptote. And if we go over here to x equals 3, we'll have something that is 8 units above the new asymptote. So that pattern that we had before, which went something along the lines of it was 1, 2, 4, 8, and let's see, 1 half, 1 quarter, 1 eighth. Now all we have to do is take all of those values, and because it has shifted up by 1, all of those get 1 added to it. And you can see they still follow the asymptote. Our graph ends up looking like this. So what are the key features? So the things from part A that are relevant to this graph. So we don't need to repeat ourselves. We certainly have the horizontal asymptote. That's always going to be a key feature. And in this case, the horizontal asymptote is at y equals 1. What else would be a key feature to this graph? Right, so this horizontal asymptote is shifted up by 1. The y-intercept is now at this new location, which is at 0, 2. So it used to be at 0, 1, now it's at 0, 2. It's been shifted up by 1. All right, let's do the same thing. Oh, I'm not quite done yet. Function notation. So we had the original function was y equals 2 to the x plus 1. I actually wrote the function notation already to help clarify the transformations. So the new function notation for this one is y equals f of x plus 1. How about this next one? Y equals 2 to the x minus 3. This is another vertical transformation. This one is a vertical shift down by 3. And so we're going to have the exact same kind of process we went through before. The difference is going to be that in this case we have a shift down. So let's move this down. I'm going to experiment on something. I saw something quite interesting there. Look, that's quite nice. I noticed that when I did a circle before, it actually completed the circle for me. And so I thought maybe it would turn that into a straight line. So now I've shifted that down by 3, and that is the line y equals negative 3. Now let's see. Grab that hand. Let's see if I can. Nope, can't do what I was hoping to do there. Oh well. All right, so now with respect to this asymptote, the y-intercept used to be at 0, 1. So it used to be 1 unit above the old asymptote. So now it's 1 unit above the new asymptote. And then we have this kind of step pattern. So these are the steps above the horizontal asymptote. And since all we're doing is shifting here, this step pattern stays the same. So this was 1 step above. Then we have one that's 2 steps above. We have one that's 4 steps above. We have one that is 8 steps above. We have another point that's a half a step above, a quarter step above, and an eighth of a step above. And we do our best to draw a nice smooth graph connecting all of those points. And you can see it looks the same each time. The difference is just in some of those properties. In this case, the horizontal asymptote is y equals negative 3, and the new location of the y-intercept is at 0, negative 2. It's moved down by 3, but it used to be at 0, 1. And in function notation, it's y equals f of x minus 3 this time. So in general, if I've got y equals 2 to the x plus q, determine the effects of changing q and in terms of key features. So this is a vertical shift by q. If q is a positive number, that means up. If q is a negative number, that means down. What about in terms of the key features? The horizontal asymptote, which started at y equals 0, moves to y equals q. And that's really the key. So this one is super important. Maybe something to consider, but not quite as reliable, that in this case, the y-intercept, which was at 0, 1, where did it move to? It moved to 0, and since it was 1, that's going to be 1 plus q. So this one is not as important because depending on other transformations that could be present, for example, vertical stretches, that one can be affected by a vertical stretch. But this y equals 0 is only affected by vertical shifts. All right, so we going on to further transformations. So now we've got a value in front. This one is a vertical stretch by a factor of 2. A vertical stretch by a factor of 2. So I just finished talking about that. Does that affect the horizontal asymptote? And the answer to that is no, it does not affect the horizontal asymptote. Oh, look at that. I didn't get my, and it's still not doing it for me. Okay, sometimes it'll give me the line, sometimes it won't. So the horizontal asymptote is still along the x-axis. So there's my horizontal asymptote. If I multiply that y value by 2, it's still at 0. So my horizontal asymptote is still at 0. My step pattern, which was 1, 2, 4, 8, 1/2, 1/4, 1/8, well, all of those values vertically stretched by 2, so now I'm going to multiply those by 2. And so to multiply those by 2, I used to be 1 unit above the horizontal asymptote. Well, now I double that. That's 2 units. I used to be 2 units. I double that to 4. I used to be 4 units. I double that to 8. Just put a scale on here just so we know we're still using the same scale as before. At -1, I was a half a unit above the asymptote, but now I'm a full unit. And now my 1/4 becomes a half. My 1/8 becomes 1/4. So you take a look at the graph and you compare it to, let's say, all the way to the original. I know it's hard to jump between those two, but certainly the overall shape seems to be the same. And some of the values we got there, for example, 1/8 became a quarter, 1/4 became a half, 1/2 became 1, 1 became 2, 2 became 4, 4 became 8, and 8 became 16. It didn't fit on the graph. But the interesting thing I want you to see here is the fact that these values, 1/4 through 8, are the same as these values. They actually match up. So as far as the transformation goes, the fundamental graph is still there. It's just been visually, it's been changed in some way. We're going to talk about that in a moment. Key features: horizontal asymptote hasn't changed, but it's always worth making note of. And the Y-intercept has moved, or it's not so much moved as it is a new Y-intercept. And it used to be 0, 1, and now this has been stretched by 2, and so it's now 0, 2. Function notation, this would be y equals 2 f of x. How about this transformation? Well, this one is a vertical compression by 2. And so what's a vertical compression going to do? Similar idea. We're going to have our asymptote. I'm not going to draw the asymptote in. The asymptote is still here at y equals 0. And so now it used to be that we were 1 point above, but now it's going to be a half a point above. It used to be that we were 2 above, but now we're only 1. It used to be that we were 4 above, but half of that, now we're at 2. It used to be that we were at 8 above, but now we're down to 4. And where we used to be at, this is now a half. Where it used to be a half, now it's a quarter. Where it used to be a quarter, now it's an eighth. Where it used to be an eighth, and now it's a 16th. And you can see we're getting really close to the x-axis there. But when I draw my graph, I end up still with that same shape. The horizontal asymptote is still at y equals 0. The y-intercept is now at 0, 1. The equation in function notation is y equals 1/2 f of x. There are a couple of questions to go along with this. So given that y equals some coefficient a times 2 to the x, where a is a value bigger than 1, what kind of transformation is this? And how does it affect key features? So first of all, the transformation is it is a vertical stretch by a. And what are the changes? Well, the horizontal asymptote didn't change. The horizontal asymptote, y equals 0, was unchanged. And that's important. Everything to do with the horizontal asymptote is important here. And the y-intercept went from 0, 1 to 0, a, because we took that 1 and we multiplied it by a. Similarly, if I have a times 2 to the x, but the value of a is a number between 0 and 1, what effect does this have? This one would be a vertical compression by, now you have to be careful how you say this. Technically, this would be a vertical compression by 1 over a. The horizontal asymptote, y equals 0, so it's unchanged. And the y-intercept at 0, 1 has once again gone to 0, a. All right, how about another set? Slightly different here. Now our leading coefficient, our a value, is a negative value. That is a vertical reflection. So what is a vertical reflection going to look like here? So once again, let me just write out my my step pattern. 1, 2, 4, 8. I'm about to write negative there, getting ahead of myself. 1/2, 1/4, 1/8. So when I do my vertical reflection, these all become negative values. So that becomes negative 1/8, negative 1/4, negative 1/2, negative 1, negative 2, negative 4, negative 8. Has the horizontal asymptote changed? No, it has not, because if you take the value y equals 0 and multiply it by negative 1, you still have the value y equals 0. So now, instead of having a y-intercept 1 unit above the asymptote, it's 1 unit below. Then our step pattern over 1, and now it's going to be down 2. Over 2 is now down 4. That's all I can fit there. And then I've got a half and a quarter and an eighth. And then, just as before, I do my best to draw a smooth curve respecting the horizontal asymptote there, and you can see I've got a mirror image vertically. How about this one? Y equals 2 to the negative x. This is a horizontal reflection. And in this horizontal reflection, now these values don't actually change. That's not what a horizontal reflection does. A horizontal reflection means that the x coordinates change. Now the one that doesn't change, the point 0, 1, is going to stay 0, 1. So the point 0, 1 is going to still be 0, 1. But for example, we used to have the point 1, 2. Well, that's going to become the point negative 1, 2, because it's a horizontal reflection. The x-axis, or the x-coordinate, gets multiplied by negative 1. The point 2, 4 changes into the point negative 2, 4, whereas the point negative 1, 1/2 gets changed into the point positive 1, 1/2. And so now that I've done this, now that I've written it this way, I realize that these are all on the wrong side. Let's see if this will let me do what I'd like here. Oh, look at that. That's nice. So I'm going to move those up there and now go back to my drawing. And so this point stays the same, but now 1, 2 has moved over to negative 1, 2, negative 2, 4, negative 3, 8. Let's see, 1 would be a half, then a quarter, then an eighth. And once again, doing our best to draw a smooth curve. I didn't do a great job there, but you know what? Give me one more chance at that. There we go. Okay, one more try. Draw a smooth curve. Okay, better attempt. And what I really wanted, the reason I redrew that was because I really wanted you to see that left side, right side symmetry between the two, to see that image, the mirror image there. Once again, the asymptote is still at y equals 0. Okay, key features. Now, something actually quite important has happened here. The horizontal asymptote hasn't changed, but I'm going to keep stressing this. The horizontal asymptote is at y equals 0. But now we've gone from something that was always increasing to always decreasing. And the y-intercept is now at 0, -1. Horizontal asymptote is still at y equals 0. As we go from left to right, this one is also always decreasing. A shorthand for this, sometimes we use up arrows and down arrows to represent the idea of increasing or decreasing, just because as mathematicians we love symbols, and also we don't usually like writing very much. The y-intercept in this case is still in the same place, 0, 1. The reason for that is here this was a vertical reflection which changed the y-coordinate, but for the second one it was a horizontal reflection which, multiplying 0, you still end up with 0. In function notation, we end up with y equals negative f of x, and for the horizontal reflection it's f of negative x. Given a times 2 to the x, describe the effects of changing the sign of a in terms of transformation. So when a is less than 0, we end up with a vertical reflection. And in terms of the key features, the y-intercept changed from 0, 1 over to 0, -1. Actually, so I'm going to change this. This was specifically for, so this is for a less than 0. And here, when a was equal to -1, that y-intercept changed. Otherwise, it follows the rule in general for these vertical scalings, which is you take this 1 and you multiply it by a. So here we've got something written in the form 2 to the kx. So what happens when we change the sign of k? When k is less than 0, we have a horizontal reflection. Oh, there's one other thing that I should mention here, which is what is the other thing that happens is this is always decreasing. And this one is always decreasing. And the y-intercept didn't change in this case, so no need to make a note of that. Now, the other thing I make a note of down here at the bottom is that when we use negative exponents, so for example 2 to the negative x, which was our horizontal reflection, that is actually equivalent to choosing a new base, and in this case it would be the reciprocal of this base, making the positive exponent. This is one of the exponent laws that we've covered, which is that a to the negative x is the same as 1 over a to the positive x, which can also be written as 1 over a to the x. So this is an exponent law, so it makes sense, of course, that the graphs have to be consistent with this exponent law. Okay, use your knowledge of transformations to describe the change for each of the following. Y equals 2 to the x plus 1. This is a horizontal shift, and in this case that's going to be to the left by 1. So a horizontal shift to the left by 1. My asymptote, taking the horizontal line y equals 0 and moving it to the left, is not going to change it. It's still the line y equals 0. But we used to have a point at 0, 1. That's moved over here to 0, -1. we used to have a point at 1, 2, but now that's over here at 0, 2. And so you can see that step pattern. Now that we've established where the 1 is, in steps by 1, so this is up 1, up 2, up 4, at 2, used to be 3, 8, but now it's at 2, 8. And then here we have a half, we have a quarter, and we have an eighth. And joining those up as smoothly as I can. Now, what about this one? We've already looked at this one before. This one is a vertical stretch by 2. So this was a horizontal shift. This one was a vertical stretch. They're very different. My asymptote is still in the same place. Vertical stretches have no effect on the asymptote. So now instead of being 0, 1, it's doubled to 0, 2. 1, 2 has doubled to 1, 4. 2, 4 has doubled to 2, 8. Negative 1 1/2 is now at 1, at a half, at a quarter. And if we take a look at those, and if I've done a decent job of drawing them, what you should actually notice is that these two graphs have the same graph. So where is that coming from? So first of all, let's talk about this transformation in general. 2 to the x minus p. So this is a horizontal shift right by p. And just remember, I say right by p, but if this was x plus 3, then of course we'd have to shift our direction. So let me clarify that. This is for p greater than 0. It's right by p for p greater than 0. Otherwise left. Hopefully I don't need to go into that much detail. And that's the only effect here. But now it says, what is an equivalent transformation? Well, what this is telling us is that 2 to the x plus 1 is the same as 2 times 2 to the x. And if you think about it, that makes perfect sense in terms of our exponent laws. 2 times 2 to the x is equal to 2 to the 1 times 2 to the x. But that means same base, keep the same bases, and then add the exponents. And just with a little bit of rearranging, that is exactly what we started with over here. All right, on to some additional transformations. And now we're just getting into actually applying this. So what transformations do we have here? First, we have a vertical stretch by 2. So that's our first transformation, read from left to right. And then our second transformation is a shift up by 1. Now the up by 1 is by far the more important one. And this is now where we try to be flexible in our thinking. We want to identify our transformations from left to right and in order. And if you're going to use this order, right? So you must use this order for transforming any point to x over k plus p ay plus q. If you want to transform points, you need to do things in this order. But we've talked so much about how important the asymptote is that you can actually start there. And it's actually a good idea to start there. So I'm going to shift the asymptote up by 1 right away, because the only transformation that can affect the asymptote is so only this. So the only one, actually let me write that a different way. Where's my eraser? This is the only one to affect the horizontal asymptote. So if we start with that, everything falls from there, because now a vertical stretch by 2, usually we're 1 above the asymptote, but now we're 2 above the asymptote. Usually when x equals 1, we're 2 above the asymptote, so now we have to normally we're 2 above the asymptote, now we're going to be 4 above the asymptote. Normally we are 8 above the asymptote, but now we're going to be 9 above the, we're supposed to be, normally we are supposed to be, I'm going to start over there. At x equals 0, we're normally 1 unit above the asymptote, which would be here. But we've got a vertical stretch by 2, so that's 2 units. At x equals 1, we're normally 2 units above the asymptote, but I have to double that. At x equals 2, we're normally 4 units, so I have to double that. Because I did the asymptote first, the shift up by 1 is already taken care of. Then, and now you can just follow your pattern. 8, 4, 2, 1, 1/2, 1/4, and all of those are above the asymptote. And there is my sketch. How about this one? Y equals 2 to the negative x minus 4. First transformation I see here is a horizontal reflection. And my second transformation is a shift down by 4. So down by 4, I'm going to take care of that one first because that's going to affect my horizontal asymptote. Down by 4, 1, 2, 3, 4. I really should have labeled this. This is y equals 1. This is y equals negative 4. And a horizontal reflection. Okay, well that's not going to affect the intercept. The intercept is usually 1 above, so now I do it 1 above. Then we used to, this would have been growing my step pattern this way, but this is a horizontal reflection. So now it's going to go to the left. So I'm up 1, up 2, up 4, up 8, and I can't fit up 16. And then 1/2, 1/4, 1/8. And making use of that, I draw my curve, and there is my sketch. We then go on to say, okay, well, what happens when we change the base? Everything we've been looking at so far here has been making use of base 2. So what happens when I change the base? Well, when I go to base 3, I'm still going to have a y-intercept at 1. I'm going to now, when x equals 1, I'm going to have a point at 3, 4, 5, 6, 7, 8, up to 9. At 2, we have 3 squared, which is 9. And then we're going to, at negative 1, instead of 1 over 2, now it's going to be 1 over 3, so that's going to be a third. At negative 2, that's going to be 1 over 3 squared, which is going to be 1/9. You could do a table of values for yourself here. And we end up with a curve that looks like that. I haven't done so yet. It's really worth reinforcing the idea. There is no vertical asymptote here. This is going up and up and up, but you can keep going out to the right. So that you're going to keep going this way, and it's going to keep going that way, but your domain is still going to be all x values. Your range is going to be y member of the reals such that y is greater than 0, so that y is above the asymptote. The x-intercept is still the point 0, 1. Sorry, the x-intercept. There is no x-intercept, so that's none. The y-intercept is the point 0, 1. The vertical asymptote, there is none. The horizontal asymptote occurs at y equals 0. and behavior increasing or decreasing, it is always increasing. And final page, this has been a long one. Complete each of the following without using graphing technology. So in that case, we need to identify transformations. First transformation, this one's going to be a vertical compression by 2. Means everything's going to get half as large. And then we have a horizontal reflection. So do either of these affect the asymptote? The answer is no, which means I still have my asymptote at y equals 0. 3 to the negative x means that it's been horizontally reflected, so the shape of it is going to be like this. And then we have to put on this compression. So for that, it helps to remember, just like I did before, what is our pattern of numbers? 3 to the 0 is 1. 3 to the 1 is 3. 3 to the 2 is 9. 3 to the negative 1 is a third. To the negative 2 is 1/9. To the negative 3 is 1/27. To the positive 3 is 27. Factors of 3 here. I'm not going to be able to fit all of them. I think I can fit on 2, 4, 6, 8, 10 if I use a scale of 1 each square. So at 0, 1, well, that's been compressed by 2. So instead of it being at 0, 1, it's going to be at 0, 1/2. Now I have to go out to the left to increasing values. So at negative 1 would be 3, but compressed by 2 means it's going to be 1.5. And then we have at negative 2, we'd have 9 because of the reflection, but half of that is 4.5. So we end up there. And then you can just go a third as much, and it becomes, of course, impossible to actually graph these with any accuracy. We use technology for that. This is just a sketch. It's a pretty accurate sketch. And we draw that. So there's our sketch. Oh, and here I skipped this step because I did it orally. I said it out loud, but I didn't actually do this one, which is that y equals 0 goes to, so vertical compression by 2 changes the y coordinate, multiplies or divides by 2, doesn't make an impact. Horizontal reflection has no impact, so it's at y equals 0. Function notation, y equals 1/2 3 to the negative x. Y equals 1/2 f of negative x. That's the new function. The domain of this one is x member of R, and the range on this one is y member of R such that y is greater than 0. Hasn't changed anything. Transformations here. The a value is 3/2. That is a vertical stretch, even though it's a fraction, by 3/2, which is the same as 1.5. Let's write that in a little bit more civilized manner. 1.5. This is a number bigger than 1. That's why it's a stretch. And then our second transformation is a shift down by 2. And that's important because of the effect on the horizontal asymptote, which is going to change from y equals 0 to y equals negative 2. So let's go ahead and put that on right away. So there we go. Y equals negative 2. And now to graph the rest. So a stretch by 3/2. Normally the y-intercept is 1 above the asymptote, so now it's got to be 1.5 above. And remember, this is 3 to the x. The next point is usually 3 units above, but we have to multiply that by 1.5, or 3/2. So 3 times 1.5 is 4.5 units above the asymptote. 2, 4.5. The next one would be 9. Multiply that by 1.5, and we end up with 13.5, I believe. Yes, that's going to be 13.5 units. 2, 4, 6, 8, 10, 12. It's not quite going to fit. It's going to be up here somewhere. So that doesn't fit on my scale. The next one is supposed to be a third above the asymptote. Multiply 1/3 by, well, it's easier to do the fraction here. 1/3 times 3 over 2. The 3's divide out, we end up with a half. And so this point ends up being a half a unit above. Then we get 1/9 times 3 over 2. And that one ends up going 2 and 1. That's a quarter. And again, we're just putting these things on and doing our best estimates. So this one is going to grow very quickly, so looking something like that. But remember, it still doesn't go to a vertical asymptote. It just gets really big. 3/2, 3 to the x minus 2. So in function notation, that's going to be y equals 3/2 f of x minus 2. The domain, x member of R, x member of the reals, range, y member of the reals, such that y, in this case, is above the asymptote at -2. And that's it for this very long worksheet.